This one is actually pretty interesting because what if using drag and drop I put a mobile robot in the air? Of course it will fall down, but graphics doesn't care about it. So graphics is like a cartoon. So you show people flying, people will fly. You show people underground, people will be underground. You show the head of a person right inside the computer screen, it will be there. So graphics doesn't care about logic. So we use another library which is of course called as the physics engine, also called as the dynamics library. So what it does is that it looks at each and every entity. So let's take this entity as an example, and it can either be a regular shaped circle, in which case my problem is easier, or it can be irregular shape. If it's irregular shape, then I will have to put a mesh around this, and the mesh will of course be a regular shape, and I will take every cell of the mesh and I will draw a free body diagram where I will add up all the forces. So that's a reaction force due to the left one, that's a reaction force due to the other one, and it's a 3D model. And I'll calculate the net force and the net torque. And using it, I will move it up as per the physics rules. Now the interesting things is that many things which were not important from a graphics or looking purpose. So just by looking at the table, you don't need what is the mass of the table, but then the dynamics needs those properties. It needs what is the mass of the table. It needs what is the moment of inertia of the table. It needs what's the maximum tension after which the table will break. Sometimes simulations are to break things. So with everything, I also need to specify the dynamic properties, the mass, the moment of inertia, and so on and so forth. Springs constants, frictional constant, everything. And if I do it for all those things, now one thing of course is that it will be extremely slow, so you need a dynamics library which works on GPUs and it does all these things in parallel. Dynamics is problematic because I cannot really calculate this reaction force independently. I'll have to look at all of them in order to calculate all the forces. Not always can it be done independently, but a dynamics library should be able to identify all kinds of parallelism over it, calculate in parallel everything up, and then simulate it up. So now it's about dynamics. Now it's all about for every entity calculating all the forces, and for every entity calculating all the torques and simulating them by that. You don't need to do it. It's done by the physics-based engine. The most popular physics-based engine, of course, we've got the Robotics, we've got the Open Dynamics engine, Bullet. So these are ready-made libraries, and they work with all CAD models, all 3D models. They just take in 3D models, calculate all the forces and torques, and do all those kinds of things, and they just show you, they just give you what are the new poses. And then a graphics library can always render in these poses. So far so good. Now one thing which we are forgetting is that we need to deal with robots. All this was good if there was no robots. Fortunately, we've got physical robots like this, and physical robots like this will have two things. One is the sensors and the other is the actuators. So now let's talk about both of them separately. So virtual sensors. There are two types. The first one we've already seen about that. It's the virtual camera. The virtual camera is what is done by the graphics libraries. So the OpenGL does that, and the other is the proximity sensors. So proximity sensor, you again have got sensors like a LiDAR, they shoot a laser beam, it goes, it comes back, or a sonar beam, it goes, it comes back, and of course the result is not at this display, it's there as a digital signal. This is also a digital signal. Now, given 3D models, a standard algorithm is the ray tracing algorithm. So the ray tracing algorithm asks for the position of the ray, the direction of the virtual ray. So it takes as input the position of the virtual ray, the direction of the virtual ray, and all the 3D models which are around. And it gives you where does this laser ray or this ray strike and come back. Of course, the reading that you will know is, you'll use is the actual reading plus a noise, and you'll never let the user know what is a noise. So you'll only ask for what type of noise is it? Is it Gaussian? Is it non-Gaussian? Of course, typically Gaussian. You'll ask what's the standard deviation, and then you'll add a Gaussian noise based on the modeling of the sensor, and that will be reported to the user as a virtual proximity sensor. So sonar is a proximity sensor, ultrasonic is a proximity sensor, LiDAR is a proximity sensor. Every sensor that you can think about is eventually a proximity sensor, and they all work on the ray tracing algorithms. So far so good. Now let me again go into the robotics, and now let me say that, okay, I need to program this robot. Eventually, what good is this simulation if I cannot program? Right now, all that I've done is drag and drop, and my dynamics ensuring that weird things that do not happen. So dynamics engine is running. The moment I put my head inside the screen, dynamics engine doesn't allow me to do that. I'll not be able to drag and drop. And if I place a robot in the air, then the dynamics engine will make sure that it falls, and if the reaction force when it hits the ground is more than the maximum bearing tension that it can take in, it will break, it will rupture, otherwise it will not break. Even if it breaks and ruptures, it's simulation, so you can always delete the object and insert a new one. It doesn't cost you, it doesn't hurt. So now let me talk more about robotics. So whenever I'm talking about robotics, I will need certain libraries, and we started robotics by reactive decision making, where my output command was a function of nearest few static and dynamic obstacles. Now this is handled by a proximity query library. So what the proximity query library does is it takes input a pose of a ghost robot, and the output will be the proximity to nearest obstacles. How close am I? So that is distance from nearest obstacles and the direction to the nearest obstacles. Now, interesting thing is, why a ghost robot? So sometimes you actually say that, okay, I don't need to decide what am I currently doing and what my current actions are gonna be. If I travel in this direction, then what happens? So you actually make a ghost robot travel, the ghost robot, and then check whatever is the proximity of the ghost robot. The other type of decisions making that we did was called as the deliberative decision making, or the deliberative planning. There, my input was a map and my output was a trajectory. And more or less, this is what it simplified as a problem. So these are the obstacles, and this is my robot, and this is my trajectory. So what do I say that? I say that this is my deliberative plan. So I make a ghost robot travel this. If the ghost robot doesn't collide and if the ghost robot's output is good, then I accept this as a trajectory. If the ghost robot collides or the ghost robot's output is not good, then I try to mend this trajectory using different algorithms. So my mantra is make a ghost robot travel by a trajectory if the ghost robot does not collide and trajectory is good, then accept, else mend the trajectory or make a new trajectory. That's what's the A-star algorithm. So all the paths from node to any leaf are virtual ghost robots traveling, and then you just ensure that the robot does not collide, the ghost robot doesn't collide, ghost robot does not collide, ghost robot does not collide. You reach the goal. Did ghost robot collide? No. Is the path good? Yes. Probabilistic roadmap. You need to check the collision between the edges. Make a ghost robot travel the edge. If the ghost robot doesn't collide, it's good. If the ghost robot collides, then it's bad. You don't add the edge. Now, this problem is called as the collision detection problem. So the collision detection problem, the input is the ghost robot and map, and output is whether it collides or not. So let's discuss the two problems. The first one is what is the collision detection problem. So let's discuss the collision detection problem over here. And simultaneously, let us discuss a very similar problem. It's the proximity query problem, because the input of both is pose of a ghost robot and a map, and the output is proximity or the collision or not. And therefore, what every simulator needs to have in parallel is collision checking and proximity query Now remember, I have still not started programming the robot. I'm still playing with the first GUI screen of a simulator. So the input is a 3D model of a robot, and I say a ghost robot. If the simulated robot cannot collide. The dynamics engine will not let that happen. It'll break, but there'll be no overlap. The ghost robot is the one that does not have dynamics property. That's why you say ghost. They can travel doors and windows. They can overlap with physical entities. They're ghosts. That's why we use the word ghost robot. So motion planning, we use a lot of ghost robot. Did the ghost robot collide? That's still okay. Did the physical robot collide? It has a very different meaning. Or the robot is dead. you'll have to pay a fine. So the output is proximity, direction of proximity, and collision or not. So basically only this is the output, and if the proximity distance is negative, that means there's an overlap. So that's an interesting problem. What it does is it takes a 3D model of a robot as a regular shape. I'm trying to draw a car and the environment. Now the worst that you can think of is that these are primitive shapes, these are primitive shape. Does any of these primitive shape collide with any one of these primitive shapes? And what's the query? And this is easy to find out. So if you have one primitive shape or another primitive shape, both are assumed 3D, then this is what is the proximity. This is all the proximity direction. So these are the two outputs, and in case they overlap, so this is the negative of proximity distance, and the proximity direction is called as the retraction direction. And there are geometric algorithms that do that. Now, unfortunately, if there are n polygons here and there are n2 polygons here, and I check between all pairs and I'm checking n into n2 operations for proximity and collision checking, and that's too costly because remember, bottles with nice shapes, tables with nice shapes, so I'll have to actually put meshes all around, and imagine how many polygons does mesh have? Too many. So N2 is very large if you need nice jazzy bodies. So those tables with nice curves, that's why we hate curves in robotics. You need to actually put a mesh, and then all the collision checking happens with that small triangle of that mesh, which is too small, and there are too many such triangles. So this becomes too large. Now, of course, what you do is let me take a 2D example, and let's say this is all the objects. So imagine regular shape. So let me actually draw in some nice shaped object, and let me draw in a table which has nice curves. So in terms of mesh, this is how I'll mesh it up using triangles. So that's a mesh. It's a very fine mesh. So there are too many. So what I could do is I could actually store it in the form of a tree where at every level I recursively divide, and at every level I only store the polygons in that area. If there are no more polygons, I don't divide them up. So that's how you actually store that up. And then you find out the region or a subtree of this polygon. So this entire map is the root that's divided into 8. You can see 4 because it's 2D. You divide it into 8 quadrants. So one of them is here, and this again you divide it into 8 quadrants. You can only see 4 because it's 2D. So x is divided into 2, y is divided into 2, z is divided into 2. That's what's called as an octree. And therefore, if you need to check for the collision, you recursively travel this tree of the area specified by the robot, you recursively travel the area of the entire map, and you see that whether there's a possibility that the two trees have some region in common and they intersect. And that's what makes proximity queries a lot more faster. So not going into detail, so I've got always a library which can take a ghost robot as input, as rich polygons, as rich set of polygons. In fact, polygon itself is 2D, so as rich set of polyhedra, and a map as well as rich set of polyhedra, multiple dimensions, and it tells me whether the two collide or not, the two overlap or not. Because of dynamics, the real robot cannot ever collide, it cannot real overlap, so it checks it for a ghost robot. And this is what is the task of a collision detection library or a proximity query library. So proximity query library, it gives you what is the closest proximity between a robot polygon and an environment polygon and the direction of it. If the proximity turns out to be negative, it means there's an overlap, there's a collision. The most popular library is called as the flexible collision checking library. It's called as the FCL. Now, there's something interesting for collision checking library. There are some objects which collide, but collision checking library is never bound to say that they are colliding because of the definition. So now, technically speaking, I take this part and I take this part and I take this part and I join them to make a robot. So they are part of the same body. Even though they are touching each other, they are colliding, but the library will never report it up because they are part of the same robot body. The interesting thing happens with manipulators. So that's your glass of water. Now, for this manipulator, this glass of water is actually an obstacle. So this is an obstacle. However, after you reach the glass pose, so you basically, the vision libraries look at this glass and they say that, okay, I have to pick up this glass, so what should be my end effector position? And that's called as a grasping server, another library. So it uses 3D vision to calculate where to grasp and pose of the end effector to grasp. And of course, you've got the inverse kinematics. Which tells you what should be the pose of what should be the joint angles to get pose calculated above. So the grasping server tells you that you've got an object like this, so it uses 3D vision to find out all the position and pose, and it says these are good grasping positions. So it tells you what should be the end effector's pose, and then of course the inverse kinematics library, they tell you what should be the joint angle pose, and then you can motion plan it up and pick it up. Now the problem is that this has two phases. One is here. The moment your end effector reaches the desired pose as calculated here, and you cannot grasp it up because the collision checking library will not allow it, then what you do is you just pick it up, you tell the library to pick it up, you do not do collision checking over here, and then the object becomes an affixment to the manipulator. So after you close, gripper, the water glass is not an obstacle. It is an affixment. And affixments will never collide. The library knows that. So the collision detection library that knows that it's a part of the robot body. Because it's part of the robot body, it does not collide. That's the only example when something of the environment becomes something of the robot, something as a part of the robot body. So imagine the object hierarchy. The object hierarchy in case of affixments, it changes from link 1, link 2, link 3, link 4, link 5, link 6, and effector. So it changes from this to this. It's one of the only examples where the object hierarchy actually dynamically changes when the program is running. So talking about it, the inverse kinematics is another library that's always there. So it's available as a service. You can just query the inverse kinematic server and you give it a request, you'll get a response. The grasping server is always running. You give it a request and you'll get a response. And that said, 3D Vision library is also always running. So now I don't want to make big statement, but still the point cloud library is still popular. And of course, you've got the 2D Vision library. That's always running. So you just make a function call, which of course, popularly it's OpenCV. So that's a library support that's always there. And therefore you program simulators in a platform where you can have all these libraries. The inverse kinematics and the forward kinematics is specific to the manufacturer. So the manufacturer will either give you all the data, which is the DH parameters, or the manufacturer will, for that programming platform, supply you with the libraries where you can call these things as a function call or as a server. So it's a server when it's running completely independently. You give it a request and you get a response.